going to tell us something about connections with integrable systems. So let's welcome our speaker.
Thank you, everyone. Thank you for coming so early in the morning, and I want to thank the organizers for inviting me to speak. I'm very sorry that I can't be there in person with you, but I hope that we'll still be able to have a good conversation about what I think is a very interesting set of problems in differential geometry. And recently, as the introducer said, making some connection with integrable systems. I don't think we fully understand it yet, but there's some intriguing possibilities for solving what's actually quite an old problem that's been around for a long time. And I'm going to give a little bit of the history before going into the new results. So, whoops. Oh, for some reason, I think I have to come back here. Yeah. I'm assuming these slides will become available, and I went ahead and put some of the. I can't put every possible reference up, but some of the references that I'll mention in the talk, starting with very early work in 50 years ago with Takagi, up through just the most recent preprint that's appeared on the archive, where we solved one of the longstanding problems of classifying certain curvature homogeneous hypersurfaces in space forms. So the background, curvature homogeneous Riemannian manifolds. What do I mean by curvature homogeneous manifold? You say that a Riemannian N manifold is curvature homogeneous if when you take any 2 points in the manifold, there is an isometry between the tangent spaces, that identifies the two curvature tensors, where Rx is, of course, the Riemann curvature tensor at the point X in M. In other words, the idea is that the curvature tensor algebraically looks the same at all points. Now, an obvious example of this is if you take any connected locally homogeneous Riemannian N manifold, because it's locally homogeneous and it's connected, it means that for any 2 points, they're locally isometric, and therefore their curvature tensors will locally be identifiable that way. So they'll be curvature homogeneous. That's a simple example. And in dimension 2, that's the only way it can happen. There's the famous converse, which says that if you have a surface that's curvature homogeneous, then the only way that can happen is if it has constant Gauss curvature, of course. And there's a very old theorem, Mending's theorem in 1839, that says that all Riemannian surfaces with constant Gauss curvature are in fact locally homogeneous. So in dimension 2, there's no difference between curvature homogeneous and locally homogeneous. But as soon as you go to dimension 3, that's no longer true. Which is basically what I'm going to be talking about today. One frequent, very common source for getting Riemannian metrics is to look at Riemannian metrics embedded in some space form, or space of constant curvature. And in fact, looking at hypersurfaces, if you take a hypersurface, an n-dimensional hypersurface in a space form of constant curvature C, we say it's isoparametric if the eigenvalues of a second fundamental form are constant. Now, by the Gauss equation, that implies that the induced metric on an isoparametric surface is curvature homogeneous, because the Gauss equation tells you that you can compute the Riemann curvature tensor directly from the second fundamental form. And if it has constant eigenvalues, then the curvature tensors will all be the same. And since there are a lot of cohomogeneity 1 isometric actions on the, say, the n+1 sphere, that is constant curvature +1, all of those orbits are homogeneous examples of curvature homogeneous manifolds. So there are a lot of those. But in fact, in 1975 and 1976, Ozeki and Takeuchi constructed a family of inhomogeneous isoparametric hypersurfaces in large dimension. And in 1981, their examples were extended by Ferris, Karcher, and Munzner. And all of those are examples of inhomogeneous curvature homogeneous manifolds. They tend to be fairly high dimension, but though, in fact, even today, these are the only known compact examples of curvature homogeneous manifolds. Are these inhomogeneous examples that that were discovered back then? And in 1988, Tsukada proved that every curvature homogeneous hypersurface is either isoparametric, so it comes from these isoparametric things, or it has constant curvature C, or and of course those are all known, or when n is at least 4, it's there's only one example. There's only really one non-trivial example, and that's a hypersurface in hyperbolic 5 space. And he showed that when n equals 3, the first non-trivial case that's still open at that time, he showed that if the background curvature is 0, then there are no examples. So that left open the case of which had remained open since 1988 of of finding curvature homogeneous things, hypersurfaces in 4-dimensional space forms with non-zero curvature. It wasn't clear whether any existed. No examples were known other than no inhomogeneous examples were known. There were a couple of homogeneous examples, but that was it. And just this year, in a preprint that's on the archive now, Luis Floyd, and Wolfgang Ziller showed that in fact for for non-zero C, and in fact the only thing that matters really, since you can scale, is you can take C to be ±1. There is in fact a 1-parameter family of inhomogeneous curvature homogeneous hypersurfaces that are mutually non-congruent. That is, for different values of lambda, you get surfaces that are not congruent. And the Ricci curvature of the induced metric has constant eigenvalues, 2c, 2c minus 9/4, and 2c minus 9/4. And moreover, aside from one other classical example, for each of C equals ±1, every connected curvature homogeneous hypersurface in Q4 is congruent to an open subset of one of these M3 hypersurfaces, C sub C lambda. That's the theorem. And I want to make a remark. And I'll say something about how the proof goes, but before I get into it, I'll just mention that, in fact, none of these hypersurfaces are complete. And by hypersurface, I mean a smooth hypersurface. And except for the initial value, the one value which you can take to be lambda equals 0, the hypersurface only has discrete symmetries. For the 0 value lambda, there's a 1-parameter family of symmetries, and this guy is actually an open subset of an algebraic variety. In fact, this M3 sub 1 0 is the unit normal bundle of a surface that's the image of an analytic mapping of the 2-sphere into the 4-sphere. And that analytic map, in fact, it's algebraic, given in this form, where U, V, and W are coordinates on the sphere. Sum of squares is 1. And you look at these algebraic functions of U, V, and W. And this gives, you can verify that this is a map in the sphere, and you can compute the Ricci curvature of the induced metric, and in fact, the eigenvalues are constant. Or they have these values. And this is C equals +1, so it's 2C minus a quarter minus a quarter. Now, one thing I want to point out is that, in fact, the theorem shows that, in fact, for every value of lambda, these hypersurfaces are the image of an analytic mapping of the two-sphere into S4, but we don't know whether this guy is algebraic for lambda not equal to 0. It's analytic. And unfortunately, the map Y lambda is not an immersion everywhere, because as you can see in this formula that I've written down, the W, that is the top coordinate, only appears to degree 2 and higher. And as a result, this Y0 has sort of a fold singularity along the great circle W equals 0. And that persists for all values of lambda. There's a crease in the surface, and that's what prevents the surface from the 3 manifold, which is the unit normal bundle. That's what prevents it from being an actual smooth global surface. It's a global closed analytic variety, but it has a singularity along a hypersurface. It's singular there. And like I said, for a long time, I suspected that this is actually algebraic for all values of lambda, and that may well be true, but the simplest possible ways it could be algebraic turn out not to work, except for lambda equals 0. So it's a little mysterious how you would find it, because they only have discrete symmetries, and that makes it maybe a little difficult to figure out what they look like, because you're trying to solve this PDE that describes the hypersurface, and you can't rely on symmetry reduction. The steps in the proof, I would like to briefly describe this. The first step is because it's a hypersurface in a space of constant curvature, you can write down the structure equations. It's algebraic condition on the second fundamental form, and so you can write down the Cartan-style structure equations for a curvature homogeneous hypersurface. And you recognize right away when you write it down that the structure equations are represent an overdetermined PDE system. So it's not clear that there are any solutions. In fact, that's one of the reasons that this case was unsolved for so long, that PDE system there was no obvious way to show that it was in fact compatible. But there's a standard way using Cartan's structure equations to figure out the compatibility conditions. Basically, you differentiate the structure equations to get more relations on the higher derivatives. So that's the second step, is you differentiate the structure equations to get and with the hope that you will eventually reach an involutive system, so that Cartan's existence theorem can be applied, and you can prove that the hypersurfaces exist at least locally. However, if you try to do this by hand, you run into a terrible problem in that the system of equations that you have to solve for the relations on the higher derivatives are these enormously complicated polynomials in many variables. And it's hard to make heads or tails of the polynomials. So in fact, what we did was use Maple to do symbolic calculations, to write down the relations and apply Grosvenor bases to the relations to find the simplest possible defining equations. You actually have to differentiate here. You have to, I mean, you know that if there are solutions, the solutions have to be real analytic because for various reasons that have to do with the structure of the equations, because the characteristic variety is empty and it's polynomial equations. So that justifies taking very high orders of derivatives. You actually have to differentiate something like 5 times to get enough relations for Grosvenor bases to work. But eventually, the applying Grosvenor bases allows you to solve the equations and find out there's only one possible set of triples of the eigenvalues of the Ricci tensor. And then the next step, unfortunately, so you have this Frobenius system that you're trying to find the leaves of the Frobenius system, and it's not immediately clear that you know anything about the structure of the leaves or their topology or anything like that. But fortunately, there's a conservation law. There's some rational function in the derivatives of the second fundamental form that is actually constant on every solution on every leaf, and that allows you to compactify the leaves of the Frobenius system and conclude that there's only a one parameter family of maximal integral manifolds, and that parameter turns out to be the value of the conservation law. Once you know that the leaves are compact, you can look at their topology. You can determine their topology because you know what the level set looks. You know what this function L looks like. I don't want to write it down because it's somewhat complicated. But the result is that when you're dealing with background curvature plus 1, the equations become can be interpreted as a flat connection on a compact surface of genus 2. And in the hyperbolic case, c equals -1, it turns out that the equations can be interpreted as a flat connection on a surface of genus 1. So with that, the compactification allows you to resolve the singularities caused by points where the second fundamental form blows up or degenerates, where the normalizations that you use to write down the structure equations break down. The compactification fills in those holes, and you finally have a compact problem, and then it's just a matter of exploiting the discrete symmetries of the problem to show that there's an underlying that these 3 manifolds are actually the unit circle bundles, when c equals 1 anyway, are the unit circle bundles of an actual 2-sphere. And that 2-sphere is analytic, but it has a crease. For every value of lambda, there's a crease along the equator. And so you don't get complete smooth solutions, but solutions with a singularity that you can't remove. But nevertheless, these hypersurfaces do exist, and we have a complete understanding of what the solutions look like, except that we can't prove that they're algebraic. They're closed analytic sets, but we can't prove that they're algebraic. or at least we can't yet. That's still an open question. And this now actually completely resolves Tsukado's problem of classifying the non-isoparametric constant curvature homogeneous hypersurfaces in spheres, because this was the last remaining case. It turned out the lowest case was the hardest case, but that's done. Now, of course, not every manifold comes naturally, or curvature homogeneous manifold comes naturally embedded in a hypersurface. Remains the problem of trying to understand what they look like in the abstract. And I'll just mention, of course, in 3 dimensions, of course, the Riemann curvature tensor is equivalent to the Ricci curvature. So being curvature homogeneous is the same as saying that the Ricci curvature of the metric has constant eigenvalues, of which I'll label C1, C2, C3. I'm actually going a lot faster than I thought I would, so have a little time. Now, if you're looking for examples, of course, the homogeneous ones are the natural ones to look at first. But it turns out that not every triple of eigenvalues occurs for homogeneous Riemannian 3 manifold. Of eigenvalues of the Ricci tensor occur for some homogeneous Riemannian 3 manifold. In fact, if you look at Bianchi's classification, which is again something from the 19th century, if you're looking for distinct eigenvalues, and that's the first thing to look for is the distinct case. There are only 2 possibilities for homogeneous things. One way you can get a homogeneous thing is if the product of the C's is positive, then there's a 3-dimensional Lie group with left invariant 1 forms omega I that satisfy these equations here. D omega I is a certain function of the C's wedged with omega j wedged omega k, where ijk is an even permutation of 1, 2, 3. Those structure equations are the structure equations of a unique Lie group, and with that particular basis of left invariant 1 forms. And now it's just a matter of just straightforward computation that you get that the Ricci curvature of omega 1 squared plus omega 2 squared plus omega 3 squared is in fact C1 omega 1 squared, C2 omega 2 squared, C3 omega 3 squared. So that's in the case where the product of the 3 distinct eigenvalues is positive. There's another way that it can happen, and that is that the C1, C2, C3 satisfy this set of inequalities. That is, 2C1 is trapped between 2 negative numbers, C2 squared plus C3 squared over C2 plus C3 and C2 plus C3. This is an open set in the space of triples C1, C2, C3, and given a triple that satisfies this condition, you can prove that there are constants P1, P2, P3, P4, and a 3-dimensional Lie group satisfying these structure equations, so that the Ricci curvature of this is exactly the thing we're looking for. The Ricci curvature of the sum of the squares of the omega I is exactly the thing you're looking for. So both of these, and these are the only 2 ways that you can have distinct eigenvalues for a homogeneous manifold. Now, one thing that's worth pointing out is that if, say, one of the C's is negative and the other 2 are positive, that doesn't satisfy either of these conditions. So So a triple of eigenvalues like that cannot occur as a homogeneous Riemannian manifold. But there are also, it turns out, triples C1, C2, C3 that satisfy both of these conditions. It's not hard to show. So, for example, I mean, it's easy to write down examples. And when you have a C1, C2, C3 that satisfies both of these conditions, then it turns out that these two metrics are not equivalent to each other. And although they have the same eigenvalues of the Ricci tensor, constant eigenvalues of the Ricci tensor, they're not isometric to each other. And excuse me. And that's a so in other words, there are you can have two homogeneous curvature homogeneous manifolds with the same essentially Riemann curvature tensor, but they're not isometric to each other. Nevertheless, a theorem proved about 30 years ago, Kowalski and Prüfer showed that if you have any distinct constants C1, C2, C3, there are local non-homogeneous Riemannian three manifolds with the eigenvalues of the Ricci tensor equal to those C1, C2, C3. So for some of those constants, none of the examples can be homogeneous. Other cases, there are a few homogeneous examples, but the homogeneous examples are very thin among the whole set, because in fact, what they show is that up to local diffeomorphism, these real analytic metrics depend on three functions of two variables. What that means is, more precisely, see that, I mean, one problem with the PDE that says that the eigenvalues of the Ricci tensor are equal to these constants, that's a PDE on the Riemannian metric, of course, partial differential equation on the Riemannian metrics, but it's invariant under the diffeomorphisms. So if you have a solution, then apply diffeomorphism, you get another solution. So in some sense, if you don't normalize out by the diffeomorphism group, then you'll be counting many more solutions than there really are, because you want to identify any two that are isometric to each other. Well, one way to cut out that dependence on the isometry group is at a point you can write down, you can say, what does the metric look like in geodesic normal coordinates? I mean, you pick a point, you choose geodesic normal coordinates that diagonalize the Ricci tensor at the origin, and you ask how many such metrics are there that are, for which, say, the standard coordinates on Rn, on R3, how many metrics are there with constant Ricci eigenvalue, constant distinct Ricci eigenvalues, for which the standard coordinates are geodesic normal coordinates around the origin. And you can compute that using their argument, although it turns out that a more efficient argument would be to use Cartan's existence theorem for diffeomorphism invariant PDE. It turns out that the space of k-jets of curvature homogeneous metrics in dimension 3 with those eigenvalues with distinct, should be constant Ricci eigenvalues, distinct constant Ricci eigenvalues, has dimension 3 times k choose 2, where k is the order of jets. In other words, 3/2 k times k minus 1. So the space of k-jets of solutions modulo diffeomorphism grows like 3 times k choose 2, which is a function of two variables, an arbitrary function of two variables. The k-jets grow like k choose 2, and so this coefficient of 3 is what justifies the 3 functions, and the k choose 2 is what justifies the ob 2 variables. So what that shows is that there's lots of solutions. In fact, that locally it's very flexible. Now, but if you're a PDE person, you want to know more than just their formal analytic solutions. You want to know what kind of PDE is this? And for that, you need to understand what are the characteristic directions and the characteristic variety. This is a little delicate because since the PDE is invariant under the diffeomorphisms, you have to, what you can only ask for is the characteristic variety modulo the diffeomorphisms. That is, you can ask, for example, is it transversely elliptic? That is, in appropriate coordinates, say like harmonic coordinates, is an elliptic system PDE? Is it an elliptic system of PDE? And the answer is no, it's not. In fact, if you take the linearization of the PDE at a given metric that satisfies the condition we're looking at with the CI distinct, what you find out is that a covector is characteristic for the PDE up to diffeomorphisms if and only if one of the coefficients CI vanishes. So the characteristic variety that which is the set of characteristic covectors at any point turns out to be the union of three lines in general position in the projectivized cotangent space. And there are three real lines. So in fact, the real characteristic variety is not empty. In fact, it's totally real. And it satisfies the characteristic variety satisfies the conditions for being transversely symmetric hyperbolic, and which is something that if you looked at the work of de Turck and Yang in prescribed curvature PDE in dimensions 3, what you expect is that you can use the theory of symmetric hyperbolic systems to show that if you have a curvature homogeneous metric in dimension 3, it's determined up to diffeomorph with distinct curvatures. I have to keep. Unfortunately, I forgot to write that down. That it's determined by data that's specified along a non-characteristic surface in the 3 manifold. And what do we mean by a non-characteristic surface? It's a surface on which the omega I wedge omega j is non-vanishing for I not equal to j. In other words, when you pull the eigenforms back to the surface, they remain linearly independent in pairs. That's what it means for a surface to be non-characteristic. And you expect the natural initial value problem for the hyperbolic system to be posed on a non-characteristic surface. The fact that the characteristic variety is hyperbolic rather than elliptic means that you're not going to have a kind of analog of the Einstein condition, where when you linearize the Einstein equations at an Einstein metric, the deformation problem is elliptic. So you expect there to be a finite dimensional space of deformations, and you expect to be able to use Kuronichi's Kuronichi kind of deformation argument that would allow you to maybe get bounds on how many deformations there are of a given curvature homogeneous compact 3 manifold. And that would be, the idea for trying to understand what the compact solutions look like would be to start at one of these homogeneous compact ones with 3 distinct curvatures and then try to deform it linearize the problem and compute the kernel of the linearization operator and try to construct a Kurenishi deformation space. But unfortunately, that's not going to work in this case because the deformation equations are hyperbolic, and hyperbolic on a compact manifold means that you're going to have to deal with problems having to do with recursion in the characteristic and the bicharacteristic varieties. And that is a very thorny problem that almost nothing is known about. So that kind of global approach turns out to be contraindicated because of this reality of the characteristic variety. So what about the case where the eigenvalues are not all distinct? If the eigenvalues are all equal, of course, the manifold is going to be an Einstein manifold, and we know Einstein manifolds are real analytic, but in dimension 3, Einstein manifolds are all constant sectional curvature, and so they're locally space forms, and of course those are all known. There's only one for every possible value of C. So the intermediate case is where you have two of the eigenvalues equal, but they're not equal to the third. And of course, Kowalski and Prüfer looked at this case as well, and proved that there do exist local non-homogeneous Riemannian 3 manifolds with the eigenvalues of the Ricci tensor equal to C1, C2, C3. But up to local diffeomorphism, these real analytic metrics depend on two functions of one variable. So it's kind of interesting that when you put this more restrictive condition of having only two distinct eigenvalues, the flexibility drops dramatically in the space of solutions. And more precisely, in the same way that I described the other, is that when you, again, because it's diffeomorphism invariant, there's you don't have you have to mod out by the diffeomorphism invariant when you're counting different solutions, diffeomorphism action when you're trying to count different solutions. So the simplest thing to do is write it in geodesic normal coordinates, and what you find out is that the space of k-jets of curvature homogeneous symmetrics with exactly two distinct Ricci eigenvalues, that has dimension 2k minus 1. So the dimension of the space of k-jets grows linearly with k, which is the same thing that would happen if you had two arbitrary functions of one variable entering into the formula. Because a function of one variable, its space of k-jets grows 1 for every order of the k-jet, and there are two such functions, so that's why you get 2k minus 1. One big surprise, maybe not so big surprise, but when you actually look at it, is that when it turns out that in this case, where you have a double eigenvalue, the nature of the PDE mod the diffeomorphism group depends on the value of C3. And it depends in the following way. First, when C3 is positive, that is the multiplicity 1 eigenvalue is positive, the PDE is transversely elliptic. And so all those metrics are real analytic in local coordinates. When C is negative, the PDE is transversely hyperbolic. And in fact, as we'll see, there are solutions that are not real analytic, solutions that are merely smooth or even have finite order of differentiability. When C equals 0, the PDE turns out to be transversely degenerate. You might expect it to be parabolic, but it's not parabolic. The Of course, you have to know what you mean by parabolic, but essentially it's not parabolic the same way that in two variables, u sub x equals 0 is not a parabolic equation because the sub symbol vanishes. U sub xx equals u sub t is parabolic, but u sub xx equals 0 is not parabolic. You just call it degenerate. And that's really what happens in this in the C3 equals 0 case. I'm not going to say much about the C3 equals 0 case in what remains, because the PDE is transversely degenerate, and you can essentially explicitly solve the equations locally. You can write down a formula for the equations for the metrics that satisfy C3 equals 0. And if you want to understand the global properties, there's a very nice 2021 archive preprint by Thomas Brooks that's mentioned in my that I listed in the references at the beginning. That gives details about what the global picture looks like for those metrics. I'm going to set those aside and now go on to so from now on, I'm going to assume C1, C2, C3 is the twos are for convenience. It turns out the formulas are better if you make them twice something. And C1 and C2 are equal, but C3 is different. And so I'm assuming C is not R, is not 0. But C could be 0, but R cannot. So first I'm going to look at the case R equals -1, which is hyperbolic, as I said, and I'll explain what I mean by that. Here's a kind of odd-looking ansatz that will actually construct all the local solutions to the PDE by reducing it to a problem on a surface. But it's on a surface with a Lorentzian metric. So if you take L to be a surface and let d sigma squared be a Lorentzian metric on L. That is, locally, you can write the metric as a product of two linearly independent linear forms. And the normalization I chose is with a 4 there for various reasons. And I'm going to let F3 be the O11 bundle over L, whose sections are the coframes, alpha 1 and alpha 2, so that d sigma is written as a factor. Basically, this O11 is up to disconnected components. It's basically a copy of R star, because basically all you can do is multiply alpha by a number and divide alpha 2 by the same number, or you can switch alpha 1 and alpha 2. That's about the only change of coframes that you can do, or you can right. So of course it's just like Riemannian geometry, Riemannian surfaces, except that it's split signature. And I'm going to let psi represent the Levi-Civita connection for this one form, connection one form. And just like in the Riemannian case, Lorentzian metrics have a Levi-Civita connection, a torsion-free connection for which the metric is parallel, and that's unique, and it's represented by a one form on this bundle. So the structure equations look like this. D alpha 1 is psi wedge alpha 1. D alpha 2 is minus psi wedge alpha 2. And then the curvature equation is that d psi is minus 2k, where k is the Gauss curvature of the metric times alpha 1 wedge alpha times the area form. so to speak. Now, you have three one forms, alpha 1, alpha 2, and psi defined on F3. And with those three one forms, you can write down this formal expression, which is alpha 1 squared minus 2k alpha 1 times alpha 2 plus alpha 2 squared plus psi squared. And you'll notice that if the absolute value of k is less than 1, then this expression is positive definite. And of course, that makes the whole thing positive definite as a quadratic form on F. And the proposition is this, that if you start with such a surface and a Lorentzian metric, L, and it has the Gauss curvature less than 1, and it satisfies this hyperbolic equation, that is Laplacian of, and this Laplacian means the Laplacian of the metric d sigma squared of the Lorentzian metric. And so this is actually a hyperbolic operator of arc cosine of k is equal to minus 2c squared root k. Then this beta metric has Ricci eigenvalues 2c minus 2. We can restrict to the r equals minus 1 case because, after all, we can scale the entire metric to make our non-zero C3, which is non-zero. We can scale to make the whole thing make C3 be minus 2, which is r is minus 1. And conversely, every three manifold with Ricci eigenvalues 2c minus 2 is exactly this form for some surface satisfying k less than 1 and this PDE for the curvature. So the point of this ansatz is that it shows that the PDE that exists on for these surfaces, for these three manifolds, actually is equivalent to a PDE on a surface, and that PDE is actually it's diffeomorphism invariant, but it's only sort of non-trivial diffeomorphisms are the diffeomorphisms that preserve a Lorentzian metric. So this is actually a PDE on a surface for a Lorentzian metric, and it's easy to show that PDE is hyperbolic, as you would expect. I'll give a quick example. I realize I only have I'm beginning to run out of time. In 2015, Schmidt and Wolfson constructed a family of complete metrics on SL2R with C1, C2, C3 equal to 0, 0, minus 2. And how did they do it? I'll just give you the answer. The family can be described with using this surface ansatz as follows. If you parameterize SL2R in this form, where the coordinates are x, y, and z, and you require that the difference between x and y is less than pi over 2, that makes this a positive number, so you can take its square root, and you identify x and y up to replacement by adding a multiple of 2 pi, integer multiple of 2 pi to x and y. Then when you take that quotient, you actually get a parameterization of SL2R for some integer k. So this actually gives you a simply connected cover of SL2R. And then it turns out that the Schmidt-Wolfson metric is just the beta metric of this guy. That is, ignore the z coordinate. Ignore the z coordinate, and just take the, 4 times the secant of twice a function of v, function of x alone, dx dy divided by cosine squared x minus y, where v is a 2 pi periodic function of x that stays in the range strictly between 0 and pi over 4. However, you don't actually need to require v to be periodic in order to have this beta metric. And in fact, the beta metric will be complete whenever v is constrained to stay a bounded distance away from the 2 endpoints of that interval. You'll get a complete metric on this open slab in R3. And there's no PDE on v. This is it gives you an arbitrary function of v. So v could be in order to define the curvature, you need to be able to take the derivative of v twice. But in fact, one of the derivatives drops out because you only have to differentiate in the x direction, not the y direction. And so you can see that there are plenty of solutions that are not real analytic. They're only say C2, and there are other examples where there's non-trivial things. Yeah. Coming to the point. In the plus case, what happens is basically the same thing, except that instead of a Lorentzian surface, you have a Riemann surface, and the natural object where the PDE is defined is a Riemann surface endowed with a conformal metric whose Gauss curvature not equal to 1 has the property that this particular expression, which you can see this where the C shows up here, that this satisfies the elliptic equation. Now it's elliptic because this is the Laplacian with respect to a positive definite metric, satisfies this equation. And there's a corresponding beta metric construction that gives all of the 3 manifolds where Ricci has eigenvalues 2c, 2c2, and that's and in fact they're all real analytic because it's a elliptic equation. There's also an interpretation in terms of pseudo-holomorphic curves. I don't have time to go into this, but you can interpret this data as defining an embedding of the surface into an almost complex form manifold as a pseudo-holomorphic curve, XC as a pseudo-holomorphic curve, and the analysis of this almost complex manifold is something that I've been spending some time on. It's an ongoing project with the hope that to be able to understand how to describe the deformations of these almost complex curves in the underlying almost complex manifold to give us some sense of what the global behavior of these things is. And finally, the big surprise is that there are 2 cases where these equations are actually connected to total lattices of type A2. And I don't have time to go into it very deeply, but let me describe what happens in the case where CR is 3 to 1. That's the positive case, so it's real analytic. What you do is write CP2 in the usual way as SU3 mod U2. And I'm going to describe how to use a holomorphic curve in CP2 to construct all these surfaces with all these 3 folds with Ricci curvatures 6, 6, and 2. What you do is basically take your holomorphic curve and do the usual Frenet frame. Look at the space of unitary bases of C3, F0, F1, F2, such that the lines spanned by F0 is a point on this curve, and the two planes spanned by F1 and F0 and F1 span a two plane that represents the tangent line to C at F naught. This is the standard Frenet frame for a curve in CP2. Then when you take the differentials of these functions on B and write them in their basis, you'll get a matrix like this, the standard adapted basis, where these two are of type 1,0, these are their conjugate, negative conjugates, and these three, the thetas are real. And let T be the subgroup of SU3, which is e to the IT, e to the minus 2 IT, and e to the IT. Then here's the proposition. The quadratic form that you get by taking omega 1,0 plus the conjugate of this guy times the conjugate of that plus 1/4 of the difference between theta 2 and theta 1, theta 0 squared. Now that's defined on B, which is actually a four manifold, but B is actually a right T bundle because the way the F's are scaled when you multiply by T, it preserves the special unitary property. And it turns out that this quadratic form has the tangent to T orbits as its kernel. And it's invariant under that. So it actually descends to this quotient, which is a three manifold, to be a metric. And where it's non-degenerate, it has Ricci eigenvalues 6, 6, and 2. And conversely, every connected three manifold with Ricci eigenvalues 6, 6, 2 is of this form for some holomorphic curve C in CP2. And the reason this is, if you know something about total lattices or equations that come from total lattices, the A2 corresponds to the Lie groups of type A2, of which SU3 is the compact version. And so this is the compact version for CP2. And finally, if you look at when in the negative case, you replace SU3 by SU21, essentially it's not quite the same picture, because what happens is that instead of looking for a holomorphic curve in CP2, what you do is look at the null lines for the Hermitian form that's preserved in 2.1, and that's a hypersurface in CP2 that has an invariant contact structure on it. And so instead of a holomorphic curve in CP2, you consider instead a curve that's a product of two real disjoint contact curves in N3. There's a natural Lorentzian metric on induced on the product of two such curves. It's independent of the action of SU21, and its curvature satisfies the conditions for the R minus one proposition. So it's beta metrics. So the beta metrics associated to a pair of contact curves solve this PDE problem. So it's a completely integrable system that works only for this ratio of C over R equals 3. For the other ratios, we don't have a way to completely integrate the equations, although we know how to write down some specific solutions. In particular, the solutions that we found that I and Floret and Ziller found as hypersurfaces, those don't correspond to the ratio of 3. They correspond to something else, two different ratios, but we still have explicit solutions in those cases. And there's probably some connection with a different kind of integrable system that explains why we were able to integrate those equations. but we don't understand that. So the connection with total lattices is evident in this particular case. It's interesting that a lot of different equations have turned out to be connected with total lattices. Natural PDE have turned out to be connected with total lattices, and this sort of gives us a key to understanding, I hope, understanding the geometry when you move to different ratios where it's not exactly a total lattice, but we can extrapolate some of the properties that we can understand by looking at these explicit cases, and hope that they will work in the other values of C. Anyway, I think I've run out of time, so I'm going to stop. Thank you for your attention.
This very interesting talk. Does anybody have any questions? Oh, sorry. Couldn't see you all the way back here.
Hi, good morning, Bryant. Piotr still speaking here.
Hi.
Hi. Have people studied Lorentzian counterparts of this problem?
Yes, there have been a few papers about this. Kowalski himself and his co-workers have looked at the Lorentzian case as well. Yes. In the Lorentzian case, there are all kinds of weird, different things you can look at because of the nullity problem that there's a sort of a non-compactness in the curvature, but there's still quite a few interesting problems. We just don't know them very well.
Another question. So these manifolds can be used as initial data for GR with a cosmological constant, positive or negative, depending upon the sum of the eigenvalues. So how well is the global structure understood?
Okay. It's not really understood all that well, actually. There's and that was what I was bringing up in the when I was talking about the problem with looking at the linearized problem around the homogeneous examples, is that when you're looking with three distinct eigenvalues, the equation is symmetric hyperbolic, not elliptic. And so global deformation problems, with compact initial manifold tend to have problems when the characteristics, when the bicharacteristics of the equation can actually sort of wind around densely in the manifold. And because singularities tend to propagate whenever along the bicharacteristics. And so, and characteristics. So, global solutions of hyperbolic equations on compact manifolds tend to be problematic. And we don't have a really good understanding of this at all.
If I may, another question about your equation. So you have this box of some function of k. Now this function k was a free. So you give initial data for this function k, or it's actually itself determined by the geometry?
You can give initial data.
Equation.
Yeah, in the elliptic case, you can give initial data along a non-characteristic direction in the that is a non-null curve with respect to the Lorentzian structure. Of course, conformally all Lorentzian surfaces are the same. So you can basically think of it as an equation for the conformal factor. And it's actually if you write it directly in terms of the conformal factor, once you've chosen null coordinates, then the problem is that it looks like a fourth order PDE, but the reason it looks like a fourth order PDE is because you don't have unique null coordinates. The null coordinates are you can reparameterize the null coordinates by an arbitrary function, and that and in order to get the invariance, write down invariant equations, you have to take that reparameterization into account, and you have to figure out how to mod out by that. There are certainly ways to do that, but didn't have any time to talk about that.
Thank you.
Okay, I think I saw one more question. We take one more question.
Hi, Professor. Thanks for your talk. And I know nothing about differential geometry, but so I don't understand the basic notions of your talk. So, so I have something to like Ricci flow and Ricci curvature. Can you explain more about this? Is there any like strong connections because they are all linked to Ricci?
Well, of course, in dimension 3, the curvature tensor is essentially only Ricci, and so it's not surprising that we talk about Ricci curvature. Ricci flow is a parabolic PDE for deforming a three manifold, and let's stick with three dimensions, a Riemannian three manifold, to make it nicer in some sense. And of course, the Hamilton's famous theorem says that if you start with a metric with positive Ricci curvature, a compact manifold with positive Ricci curvature, and you run the Ricci flow, it will essentially converge on the round sphere as it contracts. And if you keep dilating, you keep the volume fixed, it will converge to the round sphere. What we don't have here is a way to flow through curvature homogeneous three manifolds. We don't know that Ricci flow, for example, preserves curvature homogeneity. It's an interesting question. And of course, it preserves homogeneous, but
there are some works to be done, right? Like
yes,
like generally, I think we can use like Ricci flow to study Ricci curvature, right? Like
yes. I mean, it's certainly been used to great effect by Hamilton and Perlman and many others. But if you wanted to study curvature homogeneous manifolds, I think the interesting question would be: is there a flow that starts with a curvature homogeneous manifold and continues to and keeps the evolved metric curvature homogeneous? That's an interesting. I'm not aware of such a flow.
Okay,
it's not clear how you would construct one.
Some future in this kind of thing. Thank you, Professor.
Thank you for the question.
Thank you. Okay, let's thank our speaker again.
Thank you.
Thank you very much.
Enjoy the conference.
Thank you.
Okay.